Maulic K alpha line is a much shorter wavelength because the energy transition between the K lines and then it is a lot higher than copper. Copper is roughly 9 point some kilovolts of the energy transition. However, in the Maulic is a lot higher energy transition. That's the wavelength is small. So you can see that X-ray is coming from energy transition, and then what we call K alpha line is coming from excitation of electrons, the K line. The electrons ejected, and the electrons coming from another shell, whose the K alpha line is coming from right next to, and K beta line coming from second next transition, and that's why this energy is a smaller wavelength, longer than K beta line, but this is the strongest airline, the transition in the copper. So we use a specifically K alpha, the transition. But K alpha has a splitting of energy here too. So we have a K alpha 1 and K alpha 2. There are two different wavelengths of the X-ray, and K alpha 1 is a couple of them twice stronger than K alpha 2. And some of the X-ray diffraction, you need a very high resolution. You use a monochromator, and then you separate those two lines. For example, K alpha 1 and K alpha 2, from the transition of the next layer, L electron coming down here, but this one is split the energy a little bit, and then use the K alpha 1, and which is strongest one coming from the transition from here to here, and that is the wavelength here. So when you look at this wavelengths of this, it's all the transition of this, and it's all transitions of different X-ray lines. But I think a copper is K alpha 1 is most common, and other ones like tungsten and Maulic, they use sometimes L lines and then K lines. So I'm going to skip this one, but I think we have a lot of the transition of X-ray emission, and it's very useful to know the transition, not only diffraction work. I mean, there's some other types of spectroscopy work too. So when you look at the K alpha line, you can see that K alpha 1 and K alpha 2, you split these two energy, and these two different energy is, and this intensity is stronger than this. Okay, so usually you can easily cut the K beta line using the filter. Okay, so use the filter material is one atomic number smaller than your anode material. For example, your copper, and use a copper as a line. You cut this energy using nickel filter. So it's a filter nickel, and absorption edge is very close to here. So you absorb this K beta line, and you only separate the K alpha line K alpha line very strong. Okay, that's what. Okay, so you also get K alpha line. Then you have two different with the splitting energy, but most of the X-ray diffraction work commonly is you don't have a good monochromator, and those two you cannot separate it. So you have use K alpha average spectrum, which is something the weight average of the wavelengths. So somewhere in between, the peak is not perfectly symmetric, but you use also those kind of average one. But if you want to use a very, very high resolution X-ray, it's a very high resolution X-ray needed to determine the crystalline quality and those things, then use different types of monochromator. You cannot use a nickel filter and use a multi-layer monochromator, and you actually separate this and remove this one, and you only use this. Okay? But at the time, because you use another diffraction through the monochromator, and then in the case, then you lose the intensity. So we have a compromise of intensity of X-ray beam and your resolution X-ray beam. You have to compromise this. So which one is more important? You want a stronger X-ray beam with a low resolution, or you want a high resolution with a low intensity? Okay. But most of the thin films is crystalline quality is very good, and then your diffraction condition meets very easily all the grains you have. That's why even though you compromise the intensity, and then you get still very strong intensity you can get from the detector. But the powder diffractometer, powder is a lot of random oriented grains, and your very small fraction is contribute to diffraction. That's why I think a lot of powder diffraction need a large area of the a line focus, and to do that, and sometimes people don't care that much resolution, then you don't need a monochromator. So you have those wavelengths here. Clearly see that K alpha line is roughly 1.54 angstrom, but you can separate these two, 1.54 and 1.54. So we can monochromator separate this 100%, and then that's the one, and remove this. Or you don't use a monochromator to do that. You get the weighted average like a wavelength is. So depending on your like X-ray diffraction source, X-ray source, how you calculate your despacing, strain, in-plane lattice parameter, like all the information, structure information, quantitative information, you want to know what exactly your source X-ray is. Your source X-ray is monochromatically is a very clean K alpha 1, and you have to use these wavelengths to calculate all this despacing. And if you use a weighted average, like we have it's a K alpha and K alpha 2 is not separated, and you have to use these wavelengths to calculate it. So I think you have to understand what exactly your incoming source of X-ray. Okay. So this one actually tells the wavelengths of X-ray. As you can see that copper K alpha line wavelength is in the line here is roughly copper K alpha 1, and then is the 1.54 angstrom, and then you have a different wavelength you can see. Okay, so when you increase the Z number, and wavelengths get smaller because the energy transition is bigger. Okay, so that's the something. So this X-ray source is many different X-ray source people use. One major source of X-ray is a simple vacuum tube. Okay, so it's a vacuum tube, and then use a two vacuum window on both sides, and then the fixed vacuum tube. And then that energy is the flux of those things limited by cooling of the fixed target. So usually X-ray source people use is a copper target, and then you tungsten filament on top, and then you heat it up tungsten filament to generate electron flux, and electron accelerate through the electric field roughly 40 kV, or 40, 50 kV high energy, high voltage. Then you hit it, and X-ray comes out. And then, but you have applying roughly 2.2 kilowatts of energy on the very small spot. And then your cooling of the anode is the copper. It is a major factor. So you cannot go more than certain level of the cooling, because your cooling is a limiting factor to getting high flux of X-ray. So in order to overcome those things, people use this kind of rotating anode. This is a fixed tube. A 60 tube is you have a geometry of the cooling motor and then the X-ray beam. But the people use X-ray is much higher. This is the actual focus beam. X-ray is a filament, tungsten filament, and then you accelerate this one to hit the anode. This is the anode of the copper anode, and you get either one is a line focus. The shape is very similar to the length of the tungsten filament, or you have the other side is like a 4-point focus. Remember I mentioned that last week? When you hit this one, like tungsten filament to hit it, and X-ray beam is coming takeoff angle, low angle like this, you can see the line. But you see X-ray coming 90 degrees that way, looks like a point focus, right? So your point focus and line focus, there are two different types of focus. And the point focus is mostly used for single crystal diffraction, because single crystal are very, very tiny, and then you use different angular motion. And then, but most of powder diffraction, and you need a large area and then better angular resolution, and that's why it's a line focus. So when you hit this one, this anode can be hot, and then so you have to cool down, and that's the limiting factor of the actual power you can apply. So that's roughly the 2.2 kilowatts. But most of the energy, 2.2 kilowatts, goes to heat. Okay, so it's an energy transition of the electrical energy, and most of the energy goes to heat. And then just small fraction of the energy actually coming to the photon, which is X-ray. So in order to overcome those kind of like flux, like you have a brilliance of X-ray is very low, and then you want to increase this one, and one of the trick people use is a rotating anode. Rather than fixed anode like this, and then you actually use a rotating anode, which means you continuously hold the surface of the copper, because you rotate very fast, and then your cooling is much more effective. So by doing so, you can increase the like a factor of like a 5 to 10 higher intensity using this rotating anode, and this rotating anode method, which is a maximum power X-ray generator, increased if a new cooled surface continuously presents the electron beam. Okay, so this is the type of like a roughly 18 kilowatts compared to 2 kilowatts we use, like a 9 times. Okay, about factor of 10 higher flux of X-ray. Sometimes that really helps for doing X-ray because the signal to noise ratio is better, and also you have a faster you do the X-ray diffraction one. But because of this a lot of moving part, and then this maintenance is a kind of issue. And then you fixed the tube once you mount it, and you can use it for a long time. But this is one of the limiting factor. So, but I think gaining roughly factor of 10 sometimes is significant. People use that. But I think modern materials people study is you need a much stronger X-ray, and then you have a much more monochromatic beam or more coherent beam, and then those things is a direction of a lot of structural calculation, and that's why people use this is a rotating anode, basically rotating this anode continuously in heating surface, and then of the copper ring, the disc, and then it's cooled by the water inside, and that's why you get much more flux. And then so generating X-ray is a rotating anode is speed like a 6,000 RPM rotation, very, very fast rotation, and which is creating very cold surface all the time. Okay, but this one requires like a lot of maintenance, and then rotating anode is expensive, high maintenance, but most powerful lab source, X-ray source, and high X-ray flux required, and then synchrotron, which is a much higher flux of it. And anybody have done the X-ray synchrotron work, and then in the synchrotron source? No one has done that?
Not
okay.
For X-ray, so different. For irradiation.
You have done the synchrotron X-ray diffraction?
Not X-ray, irradiation version.
Oh, irradiation, okay. So you know the structural calculation or any spectroscopy work. If you use the synchrotron X-ray, actually you broaden your actual calculation tool very much. And then synchrotron radiation is the really brilliance of X-ray. It's not factor of 10, factor of 100. A factor of like a million or factor of like is much higher intensity. And then your monochromatic beam is we use here K alpha 1, K alpha 2 talking about this. And in the synchrotron X-ray, you can tune the wavelengths. It's not fixed 1.54 angstrom, but you can tune the X-ray wavelengths because there is an X-ray synchrotron X-ray coming from like a wide range of X-ray beam. And then when you get those, you have to filter use a monochromator, make a very small wavelengths. So brilliance of X-ray source is one of the very attractive thing, and several magnitudes greater than lab source. Okay, so this is one of the ring and people use, and there's several X-ray beam lines in U.S. And then it's a different beam line, has a different wavelength, different characteristics. And then one of the X-ray beam line in the Brookhaven in the East Coast close to New York, and then one in the West Coast in the Berkeley lab. And one of the harder X-ray lines we use a lot is in Argonne, which is close to Chicago and close to Wisconsin we use. And then they have a hard X-ray lines, and that's very good for inorganic material calculation, many things. So in order to really understand the materials beyond the lab source you can do, and you can use, this is a synchrotron and an argon, and this diameter is a kilometer, a few kilometers of the diameters. And then this in sector is many sectors inside, and then different the stations of doing work. Either some of them is geological work, some lines they use biological work, some lines we use inorganic materials, and then you have a lot of talented staff scientists at this beam line. So I really encourage you to actually write a proposal, for example. When you write the proposal, and then some experimental proposal, and they provide the beam line, and then you can go there, your experiment. And that is, obviously you have to pay for your travel, and you have to pay for your the accommodation. But your beam is I think it's a 1 hour cost like $1,000 per hour, or it's a very expensive beam line. And you can get a week of like a beam time, which is you can just 24 hours of the beam line, and then they use a 3-shift or 2-shift to work, and then getting some data. So amount of data you can get 1 week, maybe like the data you can take 1 year, or even like intensity is so strong, and then you can get the data instantaneously. And then so signal to noise ratio is very, very strong. So I'm going to talk about a few examples of the synchrotron X-ray, and we did later, not today. But this is the flexibility, or the stretching the pushing the envelope of the characterization of understanding of materials. So this is the X-ray source, and then you can actually easily can a couple of pages of proposal, and then you can write, and then you can get the your beam time. So this is actually the actual beam lines. So you can see all the small lines here, and those are sectors, and different sectors, because the X-ray coming through the outside the ring, inside the ring, and then you have a station here, multiple stations. They're all the stations, and then they use a different experiment, and then they have a different the instrument, and then they provide. So you just need to bring your sample. You don't have to bring anything. They have everything. So you just bring your sample, and this is some kind of the development of like different types of X-ray, and then you're coming bigger and stronger, but now more coherent beams is one of the directions. So I think this is an introduction of like a basic background X-ray source. So you have 3 different X-ray sources. One, you can use a vacuum tube, like all the lab sources use, and that's only 2.2 kilowatts maximum, which is like a regular use, most of positive fraction, and you guys do. If you go something beyond this, and 10 times more X-ray beam and lab source, it's much more inconvenient to use a lab source, because you don't have to travel, and then your array is available, and then your lab, and then you grow thin films or you grow materials, you can get feedback right away. And then, but if you want to actually characterize some of the structures, and then cannot be done by lab source, then you have a few important samples and take to the X-ray, and then you get this synchrotron, then you get the important piece of data. Okay, so you have 3 different sources X-ray, depending on what is your actually need, and you can use all 3 different sources. Okay, so now I talk about X-ray source. You have 3 different X-ray source, and wavelengths can be varied wide range by synchrotron, but X-ray source we use in the lab. Most of you guys working inorganic materials, I think the copper K line, which is the 1.54 angstrom, and that's the source of material. And the next thing is X-ray diffraction is an interaction between this X-ray and your material. So that's the basic your interaction. And then, so you have to understand that your lattices, what exactly you're looking at, and then that's why I'm going to talk about here the lattices. What is the exact lattices we are talking about? So you understand that we have 2 different lattices we're talking about. One is a real space lattice, another one is reciprocal space lattice. And then most of the concepts you use diffraction work, okay, you have real space in its imaging is good enough, most of the cases. But I think if you want to go something beyond, is more complicated structural characterization, I think you have to understand the reciprocal space lattice, because the reciprocal lattice is much easier to actually understand this. So I'll talk about these 2, real space and reciprocal space lattice. The real space is basically this is a real space. Then this is a sodium chloride structure, and sodium chloride, the chlorine here and sodium here, and this basic your unit cell structure. So unit cell, we call that atomic position, and then the lattice parameter is the A lattice parameter, B lattice parameter, C lattice parameter. But here in the cubic, A and B and C is all the same. So this is a basic your structure. But X-ray diffraction is not only getting the information of these lattices, which means your lattice parameter of the principal axis, and then angle between this principal axis, alpha, beta, and gamma. But also, you can get information of atomic positions and then what kind of atoms are located, because of your structural factor. Structural factor depending on your atomic position, type of atom, which contribute to different intensity of the peaks. And then your X-ray diffraction has two information. When you need to scan your X-ray in powder diffraction, what do you get? First, angular information, right? Intensity versus 2 theta angle. And then your angle, you have a lot of peak. But the peak position, your position of the peak in X-ray diffraction, that tells what kind of shape of unit cell. Okay, basically, your shape of unit cell is this length or angle. That's what you get most of X-ray diffraction. But your intensity information tells what kind of atoms and then specific locations. Okay, that's what your diffraction, the intensity plays a role. And then this is another structure, which is strontium titanate. And strontium titanate, you have this kind of different location of like A site and the B site, cations and oxygen in the face. And this one looks like very complicated structure. But this is also same kind of crystal structure as this kind of polonium. The polonium is a simple cubic structure. You know, polonium is a radioactive material. Polonium is only simple cubic metal. Okay, polonium is a radioactive one. And then what is the crystal structure of the iron? Do you know what is the crystal structure of iron? At room temperature? BCC, okay, body center cubic. When you heat it up high temperature and then goes to phase transition, around 900 degrees C, you go to phase centered cubic, FCC. And then you go heat it up even more, about 1400 degrees C, iron become BCC again, body centered cubic. So as a function of temperature, and the iron has a phase transition, a structure of BCC to FCC to BCC. And there's some material like copper and the gold and those materials, and no phase transition all the way to melting point, the FCC structure. So most of the metals, either BCC, FCC, or HCP, hexagonal, the close-packed hexagonal. But polonium is only material, only element, pure element has a simple cubic lattice. But looks like the X-ray feels like, X-ray diffraction feels like this one, and then this one, X-ray feels the same. X-ray also feels the same cesium chloride structure, like a cesium and chlorine. Chlorine is here, and cesium is a corner. And this one looks like a BCC structure, but it's not BCC. This lattice itself is simple cubic. So this one, and then this one, and this one, all the same simple cubic lattice. And why this one simple cubic lattice? Because this lattice is actually defined by the lattice point, not the atoms. So what is the lattice point of atom here? Is the lattice is defined by mathematical array of points, which is indistinguishable from other points, and which is identical surroundings. Which means it's not really atom. It's like a lattice point. It's like arbitrary, like a point. For example, look at this one. This one and that one is all same surroundings. Okay, right next to here, and polonium, polonium, and polonium, polonium. So you have a total 1, 2, 3, 4, 5, 6. You have a total 6 surroundings with shortest one. And second nearest neighbor, and you have second nearest neighbor here too. Okay, so there's the same surroundings, and each lattice point. So the lattice point here, same as the atomic position in polonium. Because a single atom system, you have a single atom and single lattice point, and then the primitive in itself, like simple cubic. When you look at this one, and this one, surroundings of this one, surrounding of that one is different. Okay? So that means you cannot really say that this is a lattice point, this is a lattice point. There are two different ones. Surrounding is different. You cannot use that as a lattice point. So this lattice point is sitting here, and then each lattice point contains group of atoms. The group of atoms, those two are group of atom, and that belongs to this lattice point. And another group of atom next to unit cell, this group of atom belongs to this position. Okay, so that's a definition of lattice point of this one. So you have basically you have a lattice plus group of atom forming the crystal structure. Okay, so you have a lattice point. As I said, this is like a simple cubic, but you have a group of atoms, cesium and chlorine atom together, goes to this lattice point, the overlay, then forming the crystal structure. Okay, very important to know what is the lattice, what is the crystal structure, what is the basis. Basis is a group of atom. Okay, so these are very important fundamentals of doing X-ray diffraction. A lot of things is confusing, and then you make is diffraction pattern for these three. It's all three. Okay? Strontium, titanate, cesium, chloride, and polonium all looks different crystal structure, but let's assume the lattice parameter of these are same, that your diffraction pattern looks the same. Only difference is intensity. Okay? Intensity of them are different, but actual atomic positions are same, number of peaks are same, exactly same, except intensity ratio are different. Because intensity is coming from what type of atoms in the unit cell. Okay? So these three is how many atoms per unit cell. You have how many unit cell? It's atoms here, one atom, and face center atom, 6 times half, so 3 oxygen atoms, and then you have 3 oxygen atoms, and then 1 strontium atom, 1 titanium atom. So you have total, you have 5 atoms per unit cell. Here you have only 2 atoms per unit cell. You have 1 atom per unit cell. So which means the number of atoms are different, but the lattice point here, all of them you have only 1 lattice point. 1 lattice point here, and then here. All lattice point, 1 lattice point. Okay, that's a single lattice point. That's why the primitive unit cell. And position of the lattice is all 0, 0, 0, and 0, 0, 0, and 0, 0, 0 as origin of the lattice. That's the lattice point. And then what's the basis? Basis here is 1 polonium atom, and this basis, this group 1 cesium, 1 chlorine is a basis, and here 1 basis, 1 strontium, 3 oxygen, 1 titanium. That's a basis. Okay, so the basis, and then which is same as the group of atom, and then that's an important basis. Name of Brevis lattice I'll talk about later. Is all simple cubic primitive unit cell. And this is all primitive simple cubic, a primitive cubic unit cell. And then this powder diffraction peak position is all both materials same 4 angstrom. It's 4 angstrom, 4 angstrom, 4 angstrom. The cubic material, all the, let's assume the lattice parameter is same. Your diffraction pattern, all 3 looks same. Okay? All looks same, your powder diffraction looks same, except the intensity ratio are not the same. The intensity rate is different. That's the way you distinguish these 3 are different material. Because the X-ray diffraction exactly identical, then there's no way you can distinguish this, but you can distinguish it because the intensity is not the same. Okay? So far, this is some basics of this. I mean, maybe you already know this, but I'm going to just review this, going to next level. So you can actually see this lattice, 3-dimensional lattice, form the unit cell. Okay, this is a 3-dimensional lattice form the continuous 3-dimensional array. And smallest building block we call unit cell. So your smallest building block is a convenience, we can just use a unit cell. When you define unit cell, you can have A, B, and C with 3 principal axes, and you have alpha, beta, gamma angle, like 3 angles. That's the definition of lattice. I think you already learned this one. And then you can see you have a polonium, and then cesium chloride, and strontium titanate, and then all the same kind of simple cubic lattice. And then, I mean, diamond crystal structure, this is not the same lattice, because all the atoms and then different location, but the diamond cubic, they're different. Okay, so now we have some kind of fundamental basis of lattice, and then this lattice, how many different types of lattice? Because when you grow your thin films, you grow materials, and you belong to one of these lattices, and then you have crystal systems, and that's the way you can distinguish. For example, when you grow your thin films, you're strained. Okay, you have a cubic material, perfect cubic. And you grow thin films, you elongate it or you compress it, and you change the symmetry of it. Because symmetry is a cubic to tetragonal, and cubic to rhombohedral, cubic to other symmetry. And how do you actually determine this symmetry of this? By X-ray refraction. So I think we look at this lattices, total 7 different crystal systems. Okay? You defined 3 principal axes, and plus you have angle. So highest symmetry, starting from here, cubic lattice. Cubic is A, B, and C, all same. Angle, alpha, beta, gamma, all same 90 degree. And that's cubic lattice. And then your tetragonal, you're starting from cubic, your kind of distortion start. Okay, how your distortion start? You have a cubic lattice, you just stretch it uniaxial. You uniaxially stretch it, you uniaxially compress, then you actually uniaxially compress, uniformly expand in biaxial direction, then make tetragonal. Tetragonal, A and B is same, but C are not the same. So that's your tetragonal. And then your orthorhombic, you have a stretch one way, then one more time this way. Okay, you have one stretch, one that way, but your orthorhombic, orthogonal, all the principal axis, 90 degree, 90 degree, 90 degree, all orthogonal direction, and then you get A, B, and C all different, and this angle all the same, 90 degree. So the orthogonal system. And you go from here to here to here, you accelerate diffraction and start to see more peaks. Okay? So why you get more peaks? And then here, all the peaks coming from plane between this plane, or front and back plane. This is a 1, 0, 0, 0, 1, 0, 0, 0, 1 plane. All 3 different planes. For example, you have a cubic lattice in this, something like this, and this, all equivalent. So that means they contribute to a single peak in the cubic system. But you have stretched this way, this one and that one, same, but this one is different. So the different one give a different value of X-ray refraction peak. So that's why your tetragonal, you get another additional peak. And then this one, you set splitting peak, another one, you have more peaks here. So you can actually determine the position of the peak, and then number of peaks splitting, you can tell what kind of X-ray diffraction work is. And then you have another distortion. The monoclinic distortion is a shear. Okay, shear of the cube. Okay, you actually shear a cube. Basically, when you have a cube, rather than it's stretching this way, one directional shear, make a shear is one angle is not 90 degree. So the monoclinic, or you have another shear is rhombohedral, make a corner of the cube and stretch it. Let's make a rhombohedral and make this kind of rhombohedral unit cell. Okay? So you have rhombohedral and all these things and different actual peak positions and number of peaks and due to splitting. And that's the way you can determine X-ray diffraction work, or the positive diffraction. And then you have further split of the lattices from crystal system, total number 1, 2, 3, 4, 5, 6, 7 crystal system, and divide it to 14 brevis lattice, which is a cubic lattice, simple cubic, primitive, body center cubic, face center cubic. You split the multiple different ones. Okay? So if it's any of your lattice you're growing belongs to one of the 14 brevis lattice. But you have more details of the symmetry operation, you get 230 space group. Okay? And that is much more complicated, and I'm not going to talk about this. But up to this point, you have many different crystal structures, and it belongs to one of those. And then your material, how you distinguish your crystals you grow, and then by X-ray diffraction, I think that's a very important piece. Okay, so this is a 230 space group. I don't think you're going to remember all these things, But when you read your paper, a lot of papers like R3N, and then here is a P22, and then sometimes you have a C2. You have a lot of papers talking about this different space group. And then it's worth to learn this one because, as I said, polar metals in the beginning, I talked about polar metal, and then talk about initially PB, Mn, whatever C2. This is all the space groups and all point groups. And you see here, this one point group and space group, and then 230 space group, and then your point group is worth to know, but I'm not going to talk about all these things. But I think if in order to really understand the structure, understand the other types of characterization, even like optical measurement and all other measurement, ferroelectricity, magnetism, and superconductivity, and then it's worth to study this symmetry operation of the basic the structures. And then I think it's very useful, but I'm not going to go detail. This is beyond this lecture because it's not really lecture for structural of the space group lecture. But I think it's very important to the scope of work and then what is the structure is. Okay? So I mentioned first, I talk about X-ray source. 3 different X-ray source. I talk about your material belongs to one of those. Okay? So the X-ray refraction is the interaction between your material and your X-ray source. And if you do very simple operation, any measurement, any calculation measurement, you have whatever stimulation, external stimuli, or your response. You measure the response by something stimuli or something incoming whatever source. And X-ray is incoming X-ray. You measure diffracted X-ray, only changing of the geometry of sample. That's all. That's it. It's very simple. X-ray is changing the geometry or location of the sample. In powder diffraction, just the one angle, theta to theta angle. In X-ray beam is fixed. X-ray beam doesn't change. And your change of this, change of the detector, and then that's all. Some other measurement, and then you have different types of stimulants, like your mechanical property measurement. What do you apply? You apply load, you put it in some load, like putting weight, and then measure elongation. Okay, how much elongation? From those you can get Young's modulus, okay, elastic modulus, and tensile strength, or you get any kind of information. Your transport measurement, what do you apply? You apply current, you measure the voltage drop. Okay, that's what you do. In Hall measurement, you apply the current and apply magnetic field, you measure the voltage drop. That's what the Hall measurement. So all the measurement technique, you apply something, you measure the response. But X-ray is so simple. You apply photon, X-ray beam, measure the diffractive beam, but changing the geometry of a sample. But geometry of sample, you have only one geometry, one angular freedom, which is powder diffraction, but you have 3 more degrees of freedom that give a force of refraction. Okay? So X-ray refraction, as I said, you have an incident X-ray beam with 3 different types of X-ray source I mentioned, but the interaction happens is incident X-ray and lattice. Okay, your lattice, your crystal structure is one of these, or one of these, or one of these, and then depending on what's the definition of this, and then you can use simple as this kind of definition, or as complicated as this definition of your crystal, and then your X-ray refraction interpretation is different. It's much more complicated and much more the time consuming, but all can be done by this way. Okay, so now talk about those things. And next one is, okay, if you have an interaction between this one with X-ray, what exactly happened? And that's what X-ray refraction is. So X-ray refraction is we have to understand the wave. X-ray is this kind of wave, electromagnetic wave, and this wave interact with this the matter, and you have to understand that it's a superposition of the waves. In superposition wave, you have this kind of X-ray beam with the same kind of phase or out of phase, depending on in phase arrow phase, you have constructive interference or destructive interference, and that's the basic idea of X-ray diffraction. Okay, interference of this. So interference X-ray diffraction is a very simple way to describe by this Bragg law, and Bragg law looks like a real space interpretation, not dispersed space interpretation, real space interpretation. As you can see, atoms has a periodic array of atoms, and these all the atoms, but this atoms is an interaction between X-ray in the atom. It's not the interaction between nucleus and then actually the electromagnetic wave. It's more like the electrons, surrounding electrons interact with the incoming X-ray. So you scatter because you have electrons around the X-ray, like the atoms. When your electron comes in, it scatters these electrons around, and then they interfere, and another wave comes out. So all the wave coming from the electrons surrounding atoms then collectively interfere, collectively actually contribute to this. So for example, this is an image of this, and all the atoms surrounding electrons, okay? All the electrons surround. And those things interact with the waves. All the waves interact with this, and then all the waves contribute to actual diffractive beam. So here, looking at this atom and that atom, incoming X-ray, when you draw the line here, so all the same phase. Okay, this is a 0, and here is a peak, and 0. You have everything in phase. Okay? But when you're in phase, when you actually scatter this one, and the scatter beam has some path difference. Okay? Your path difference. So you travel, this one travels longer distance than this one. And this one, even longer travel distance than this one. Right? Okay, longer travel distance. How much longer travel distance is this one plus this one? Okay? So additional ended up this position and that position exactly same starting point, but this one has traveled a little longer than this one. So depending on this length of this path length, and then it can be constructive or destructive. So if this travel length is exactly one wavelength, then you get this one. But it's not, then you get this off-center, phase shift here, then you get destructive interference. That means you have very sharp intensity peak when this condition meet. This condition meet, this path difference, these two, is actually 2D sine theta. Is a 2D, is a D spacing between these two. And sine theta, this angle, equal Bragg angle, sine theta, and that is actual path difference, but you have two of those. So 2D sine theta, same as number of wavelengths, either 1n, 1, 2 lambda, 3 lambda, you get the constructive interference. That's why you get very sharp peaks every certain angle, which is meet path difference 1 lambda, 2 lambda, 3 lambda, but this angle theta actually changes that. Okay, so most of your X-ray diffraction is require just this is enough. Most powder diffraction you do not need beyond this, because your powder diffraction, okay, I want to know what the D spacing, and then D spacing of particular peak position, and you can index it, what it is. Maybe you're happy with that, most of powder diffraction. But to do more understanding of structure, I think you have to go beyond this. So you have a Laue equations, and then you have diffraction work, but now we need to understand reciprocal lattice. Okay? So let's talk about reciprocal lattice, what it is. And then your crystal structure looks all different. Diamond and then a graphite all looks different, but all with the same element of carbon. But how can you distinguish all the three? And then chemically identical, but structure all different. And the way to do is ideally, you can X-ray diffraction can tell what the structure is. So let's see what the real space and reciprocal space means. And the definition of reciprocal space, I'll talk about that later. But let's see what reciprocal space means. So real space is atomic position of these atoms located. And then reciprocal space of this one is between these two planes. Okay, these are these two planes, and they correspond to these two. And you have another plane. This is 100 plane. Is 100 plane correspond to here. But you have a half of this. Okay, this spacing here, half of this, and this another 002. Okay, what they mean is your D spacing is longer one is here, and shorter one is here, and then twice longer. And then 004, 003, and then here, which means 3 times longer than 001. And 004, you get here. So your building reciprocal lattice is inverse. So the real space longer and longer, and then this reciprocal space is shorter and shorter, and then this is a reverse. That's a reciprocal space concept. Same thing here. You get this kind of 001 and 00200. You get this extension of this. You get building this one. So basically, you make all these angles, you get this kind of reciprocal lattice. Okay, what all these points correspond to planes. This is not actual atom position that correspond to all the planes. So what that means is each of them is this 100 plane and 200 plane, 300 plane, and the 110 plane, 220 plane. So these are all the corresponding planes. And the same thing here. Look at pseudo-cubic epitaxial layers when you grow this kind of structure. For example, this is barium titanate. Once you grow barium titanate, so this one is exactly the same example of barium titanate thin film grown on strontium titanate. Okay, when you grow barium titanate, that is big. So when you grow it compressively, you compress this strain, elongate it. Remember this? So when you do that, and then this is the actual reciprocal space looks like. What they mean is you have this lattice, blue one, okay, this unicellular of strontium titanate, unicellular of barium titanate. And unicellular of barium titanate, this color of this one is cubic. The cubic one is outside here, blue one. Okay, it's blue one. And then when you have this longer one, in this direction it's same, so this direction is identical. But this out of direction, you get the longer one, it shows smaller one. Can you see that? So the longer lattice in the reciprocal lattice shows a smaller, and this particular one, this one, corresponds to 100 plane, this plane. And this one, blue pink one, coming from this lattice, a longer lattice. Okay? And then next one is blue next one here, coming from half of this, which is a 200, which I say is 200. This plane. Okay? This plane corresponds to the 200. So that's a 200 shows this plane. And 300, 400, this is all coming from substrate material. And then this pink one coming from this barium titanate layers. But in the plane, you cannot distinguish it because in the plane here, the same line up here. They're all lined up. Okay? So what they mean is, you can image it. You can image just looking at this. Okay, I just image this one. Then I know exactly this material. Okay, image, for example, I want to image that one. Okay, just image this one. Then I know this one lined up, perfectly lined up. Once you line up this one, then I know this is coherent, okay, fully coherent. And then I know this one, the position is split. That means lattice parameter of this, lattice parameter of this one are not the same. But if it's incoherent, okay, incoherent grows like this. Look at this incoherent, because barium titanate does not grow coherently like incoherently. Which means it's not only vertically different, but in plane is different too. So what that means is 1, 0, 0, that direction plane between this one and that one is a blue one here. Okay, this is a blue. Okay, this is a 1, 0, 0, and there's a 1, 1, 0, and a 0, 0, 1. So this one corresponds to this lattice. But the barium titanate one is much bigger lattice, both in plane and out plane. Then you get in plane is a bigger. So that means your reciprocal space lattice is smaller. So that means it's smaller here. But this one is all lined up here, smaller. But outer plane is larger than this one. That's why it's actually smaller than this. But position is not that far from here, very close to each other compared to this. Why? Because this one elongated, much more elongated, and then that's why the difference gets bigger, and then this distance further. Okay, so that means you actually see this focus lattice of relaxed film and then coherent film, and then looks like this. So when you do X-ray diffraction work, is people do reciprocal space mapping. To map out any of these regions, I want to map out this one, okay, like this. Map out this, or map out this, and these two, this is H direction, because this is H, because H direction is that direction, and this L direction is that direction. So we plot this reciprocal space lattice, cut the slice of reciprocal space, H direction and L direction. From those, whether these two lined up along this direction or off center, that tells coherent, incoherent, without going through all the calculations. So there's a simple way to do that. Okay, so let me just show you the real data here. Okay, this real data. I think later I'll talk about very similar type of many diffraction I will show you. Look at this. This one is basically H angle here. H, basically same thing. Your H and this L. L and H. Okay, same as H and L. Can you see that? Okay, so you're looking at this one, and then this one is lined up, vertically lined up, or off center. Which one is that? It's not lined up. But how about this one? It's lined up. So that means the same kind of material, and this is completely strained layer. Once it's strained, perfectly strained, and these two layers strained. But this one relaxed. So actual structure here, you have this kind of structure, one layer strained, one layer relaxed. And this strained layer is lined up on top of each other. Okay? And then relaxed layer on top and not lined up. So draw the line here, perfectly line up, but this is off center. But you have, for example, everything is strained, you get this kind of curve. Okay? All three layers line up, then you get this kind of one. But this one and that one is all coherent to line up. Then everything like this. But in here, one layer relaxed, and then this one, H value is not the same, off center. You understand this one? Okay, this is a very basics of this part space mapping of your crystal thin films you grow, and then this information can be done very easily by your diffraction work. Okay, so your relaxed case, you have this one. It's not perfect lineup. This is lineup. Can you see that lineup here? Straight. This one, that one, that one, that one is all same H. And this one is this one and that one is not vertically lined up, it's off-planar. You get it? Okay. So that is thin films we talked about, and then reciprocity mapping. Okay, so that's the one way we can determine it. So what time is it? Just 1 second. All right. So far, I talked about reciprocity mapping. And this reciprocity mapping also can do this kind of stress structure. When you grow thin films on your substrate, your thin film substrate atoms align this way. But sometimes your films does not grow perfectly line up like this, line up like this, all lined up. Sometimes it's tilted. If your tilted grows, you will see this one, everything tilted. The tilting can be measured by using same kind of reciprocity mapping too. So you'll see that you have this thin film, it tilted with respect to this one. Okay? So you get measure information of tilting of material or your coherent, incoherent one. You can measure this kind of coherent, incoherent growth and relaxed layer and strain layer. You can determine it. You can measure tilting of the measurement. And then you also can measure mosaic spread. Okay. What the mosaic spread? When you measure, grow your thin films, all the grains not perfectly lined up. So you go outside here, a lot of buildings, brick buildings. Can you see the brick buildings? Okay, brick buildings. So brick buildings and build the brick buildings. Masons actually put the bricks line up very nicely. So most of the bricks here very well lined up because they did a good job to line up. But sometimes your brickwork is not good. Sometimes mortar, you put it in more and less, the bricks like this. Okay? Bricks line up this way. Then you look this front side, looking the bricks. It's not beautiful because they line up like this, a zigzag shape. That's what we call this a mosaic spread of the crystalline. So you have, when you grow your thin films, all the grains, some kind of tilting of this, because the nucleation of each grain nucleate differently, different location, and also sometimes dislocation. So you have a little bit of tilting of this. They're creating this kind of real structure, shows mosaic spread. You have this kind of mosaic spread, and each grain contribute to X-ray diffraction differently. Okay, but this one is not only few grains; it's billions of grains. So the range of spread, this kind of brickwork. Okay, in that case, your actual this one is spread in that direction. This is what we call mosaic spread. You have mosaic spread like this, and then you get your wide range of peak width. And then your beam, looking at this one, okay, some of them, and the very sharp peak, one of them is broad. Can you see that one? Okay, this one is very sharp, one of them is coming from substrate, and then this one is very broad. So why you have broadening? And this broadening coming from this kind of mosaic spread. And same thing here, very sharp, you have broadening. And then this broadening is coming from the mosaic spread of your material. So you have a more spread, then your mosaic spread is poor. Like when you go brickwork is a lot of bad mosaic work, and you have this kind of one, and you see this kind of broadening. Okay? So now you have a reciprocity mapping, your structure, getting a lot of information. One, your material is strained or relaxed. How much relaxed, how they're strained. Then you get this kind of information from this kind of RSM, reciprocity mapping. Okay? And then your material is how much you're tilting of this. And tilting can be measured, this kind of structure, tilting, can be measured this way. Or you can measure this mosaic spread, how much of your mosaic spread, all the grains, and then you get this kind of broadening, and then you know how much broadening. So, when you do all your diffraction work, it's not two-dimensional work. Your all powder work is basically ignore H. You only measure L. L means your X-ray detector only scan along this line. When you scan line along this direction, okay. When you throw along that direction, look at this. From here to here, just scan this way. You have no peak at all. Okay, nothing, no peak, and then your peak comes out very weak peak. You have a peak here, thin film peak shows up. Then you go here, very strong peak, sharp peak comes out, and then disappear. So your X-ray is with this direction. L scan along this is basically 2 theta angle. So your information, your X-ray diffraction is only one-dimensional information. Your one-dimensional information is very limited information about your sample. So you want to get three-dimensional information. Basically what you want. Your structure is three-dimensional information. In order to get those information, you need this kind of reciprocal space understanding. So just looking at this, just draw the line here. Draw the line here. You get peak. Nothing, one peak and peak. But you draw the line here, draw the line from here to here, you miss this peak. You understand? Your powder diffraction, I just want to run powder diffraction like your thin film looks like this kind of thin film, okay? You scan along that direction, you will miss this. So then you don't see the thin film peak. Okay, then we have a, looks like, oh, we have no thin film. But it's not. Thin film peak is somewhere around here, but you are missing. So you have to get full two-dimensional or three-dimensional information. You can capture this. The two ways you can capture this. One way, you scan not only L direction, you actually scan slices of these, many, many scans. Many scans, you actually make a two-dimensional one. So it takes this kind of scan, takes overnight scan. So one scan like this, you multiple scans, how dense scan along that direction. You have a line, one line, another line, another line, another line. So you get many, many scans. Then you mapping two-dimensional map. Or one simple way to do, people use this two-dimensional detector. Detector is not one-dimensional, like point detector. You make a two-dimensional detector, you can capture the whole thing. Okay? Well, that is another detector technology. Is you go synchrotron or in the lab source. You have a detector shape. I think I showed you previously some of my picture. Detector like a circular shape or square shape or CCD camera or like some MOS device which can actually detect whole thing. It's still X-ray detector, but X-ray detector is not only one actually point detector, it's a two-dimensional area detector. Then you can capture a lot of these things. Okay? Now you understand? I think maybe it's still very hard to grasp this until you practice this, until you use your own material and take it and do it. But I want to give you some introduction of what kind of structural determination you need for your thin films. That's why I'm going to that. Maybe during the break, I think I'm going to talk about this whenever we come in more specific example you want to talk about your samples, and I can discuss. But I think this is very important for structural information. Okay, so this is a mosaic spread. You can actually see how much of mosaic spread. In this direction, you get information, your size, your grain size gets smaller, grain size gets smaller and your thickness gets thinner, your Bragg is the interference of this cannot cancel completely. So we have only one atomic layer, one unit cell, 10 unit cell, 100 unit cell, millions unit cell. Your cancellation of this not perfect. So when you get smaller number, that's why you get the peak broadening, which is we call Scherrer formula. I think it's the one Scherrer formula I talk about that later. I think that is a peak broadening coming from size. Your grain size, film thickness, the size effect is a peak broadening coming from here. Okay, so you have a broadening. Peak is broadening in along that direction. Peak broadening along that direction give a different information. And different in this direction of information is a mosaic spread. And this information is size distribution, or you get different lattice parameters. Okay? You get lattice parameter different, and then you get this kind of information. That means you have a lot of strain gradient. Okay? You have a strain gradient, which means lattice parameter at the bottom region and top region, your strain gradually less. Then your outer plane lattice parameter is a varies. Your outer plane lattice are varies, and this peak is a broaden. So most of your X-ray refraction, your thin films, single crystal substrate, very sharp peak and very narrow. But your thin films broadening both that direction, broadening that direction. And the broadening of this is contributed by different factors. It's size or crystalline quality or strain or all this information, and that's coming from. Okay, that is constant variation, as I said. Okay, you have, this is the exact information. You have information of this lattice parameter small, medium, and large. Because the strain relaxation is different, for example. Okay? And then your strain relaxation different, you get the different lattice parameter, then you get the elongation that direction. Can you see that, elongation? Because this one, because this shorter, short means this cross space position is longer. So that means that this part contribute to, actually, this long contribute to bottom here. Can you see that? And this one, long, contribute this position. But that means this one contributed here, and this one contributed here. You get it? Do you get it, this one? So this focal. Can you hear me? I think battery is out. Let me just change my battery. Maybe it's a good time to take a break. Come back. Yeah. Good idea? Okay. Could you change the break? And then roughly hour 20 minutes. I take the time to break. Come back. That's not true. Your peak is somewhere. Your detector, your sample stage cannot access those areas. You understand? Let's take a break and come back in 10-15 minutes, and we can finish this. Sounds good? Okay. So I give us some introduction of reciprocal space, and then for most of the thin films. But let's just go back to the very basics of what is reciprocal lattice and why we bother. I think that's something. So reciprocal lattice, I mentioned that the real space and reciprocal lattice, and then vector algebra. I think you all done strong in math, and convenient for describing the otherwise complicated diffraction problem. Okay, diffraction problem is simply you have a one single perovskite simple like a cubic unit cell. Okay, you have a cubic unit cell. How many planes you can draw within one unit cell? How many planes you can draw? Distinguish all of those. How many can you draw? Maybe you can 100 plane, 110 plane, 110 plane, 111 plane. Okay, you have up to 3. Maybe you can actually draw very easily. You can see it. Then beyond this, you're drawing more and more unit cell, so messy, so you don't know what it is. Is that true? Okay, so you really cannot describe. It's because of X-ray diffraction is basically coming from arbitrary like planes. Okay, the HKL plane is a diffraction plane, but plane does not exist. Plane is actually arbitrary draw something on the real X-space lattice. But you cannot draw many planes in the unit cell. So that means when you try to describe your diffraction work in the single unit cell cubic, I want to draw 110, 110 diffraction, a 111 plane, the 125 plane. I want to do all different planes. Very complicated, almost impossible to do that, doing so. So this response space actually allow you to describe very complicated diffraction problem. Okay? So that's something, your motivation to learning reciprocal lattice is you complicated diffraction problem very easily, and then not just learning this one, but you can actually explain somebody your material diffraction conditions and your material structures much easily. That's why it's a very important learn, and this reciprocal lattice. And this one also offers simple approach to handling diffractions in vectors. Okay, so we use vectors, and then this is all the math. But once you know the geometry of this, you can actually construct what we call Ewald sphere construction, and then meet the diffraction condition in the vector, and then explain so beautifully, so easily. Okay, so I will explain later. Anybody know the Ewald sphere construction? Anybody learn Ewald sphere construction? How many know Ewald sphere? Okay, so we'll talk about Ewald sphere, which is geometric description of your diffraction condition, very simple way using reciprocal space lattice. Using reciprocal lattice permit the analysis of diffraction problem cannot be accessed by the Bragg law, which is off-peak backscattering, all these things. Bragg is so simple to explain it to college students, maybe freshman students, you can learn. But you guys, PhD graduate students, you are learning research, and you need to more than Bragg law. Okay? So a lot of diffractions cannot be described, cannot be accessed by Bragg's simple law. And the reciprocal lattice is important for all phases solid-state physics, undestined concept useful, and then just itself. But I think this is maybe too much. I'm talking about this one. So the concept of reciprocal space lattice is we already learned the solid-state physics. Your Kittel's book, and you have this one. Everybody's seen this. But sometimes people do not grasp this one is in physical meaning of reciprocal space in diffraction work. That's why I want to make this connection. It's a mathematical description of reciprocal space and then actual physical meaning of this in diffraction. So let's consider real space unit cell like this unit cell, this real space. You have vectors, A vector, B vector, and C vector, which describe your real space unit cell. And reciprocal space lattice is actually described by A star, which is reciprocal space unit vector, and the three-component unit vector A star is B cross C divided by A dot product B cross C. Okay, what they mean is simply, I think this I don't have. I think it's easier to draw by hand than doing it, but let's try to without doing it. See what happens. So it's like B cross C. Okay, B cross C is you have a B and C. Okay, so this one direction of B cross C is perpendicular to the plane formed by these two vectors. You get it? So the B cross C is, what is the B cross C? You have this kind of two vectors. Too heavy this one. Get two vectors like this. And B cross C is a B and C you cross is the right hand, right? You know that? Right hand, this is the direction of B cross C. So that means you make a plane formed by these two vectors, and then perpendicular direction, that's a directional vector. Which means I can describe plane formed by these two vectors. All the X-ray diffraction work is scattering vector normal to the plane. So that means you want to find out normal direction of the plane. That's what we care in the X-ray diffraction. So that means, okay, B cross C, I define it one perpendicular direction. At least I can describe the direction of the plane normal. I know plane normal, what direction. The problem of non-orthogonal systems like this, non-orthogonal system, and the plane normal is not the C direction. Normally in cubic system, a cubic perovskite, cubic structure, and C direction is perpendicular to B cross C. You get it? So all orthogonal system, no problem. It's orthogonal system is especially orthogonal cubic system. All the perpendicular direction is same as the plane. Is a B cross C is parallel to this one. But this is a non-orthogonal system, and then this direction C star is formed by A cross B. Okay, so A cross B forming the C star, and then you have to look at this order of this, memorize this one. Okay, I think the simple memorization is you always coming ABC, ABC, ABC sequence. You get it? So that means A cross is coming A, B, C. B, B, C, A. So you look at the ABC, ABC, ABC. You just make up some section of those things, and there's a C, A, B, C, A, B, C. So you have a section of it. So easy to remember that way. I think that's the way I teach students. And then here, C cross A. You don't want to mix this one, A cross C, the C cross A, because that's the other direction, the opposite direction. So B, the C star is A cross B going that direction, A to B. That's why C star. You get it? Okay, so now we know all the perpendicular direction of the plane is reciprocal space vector. But describing the plane, you need the two information: direction and magnitude. Okay, what is the magnitude of vector? The magnitude vector is very important in reciprocal space lattice. The magnitude vector here is divided by A dot B cross C, which is the volume of this. Okay, the divided volume is normalized by volume. Okay, normalized volume. But look at the B cross C, and then you have B is long and A is very long. Okay, B long and A very long, and cross product here very long. Then this value is going to be, the magnitude of this magnitude going to be what? It's going to be small or big? Let's draw something. This is not ideal case. Let's try to, let me see, I have to draw something. Let's see, you have a unit cell of A is very long, B is very long, and C is very short. Okay, C is very short. Then you cross product A and B is a long one, multiply two of those, then this value is going to be very big, right? Very big. But the length of this vector here is very long. But real space, actually plane is roughly this plane and that plane, direction is short. You get it? C direction is very short. So that means is you get this value of this reciprocal of this length of that plane. Okay, I have to draw something more realistic one because this is not the perfect one. So you have two information reciprocal space. One information is your cross product is this cross vector is defined by that way. But the two information you get is actual vector direction is perpendicular to the plane, and length of vector reciprocal of the d spacing of that plane. Okay. Two information is no direction of reciprocal vector defined by r star, which is any arbitrary HKL plane. It's a 100 plane, or 110 plane, 235 plane, 157 plane, whatever plane. The direction of the plane is perpendicular. That direction of it perpendicular to this reciprocal space vector. Okay, and the length of this vector is reciprocal of your d spacing. So that means you have tetragonal unit cell. Okay, tetragonal unit cell is 2 angstrom, like a 4 angstrom, 4 angstrom, and then that direction is 8 angstrom. Okay, your 8 angstrom. Then your reciprocal space lattice in that direction, reciprocal lattice 1/4 angstrom is 100, which means a quarter angstrom inverse. Okay, remember that? So the reciprocal because the unit is 1/4 angstrom. So that direction 4 angstrom, 1/4 angstrom is a quarter. Okay, 0.25 and then 1/4 angstrom, the reciprocal angstrom. But this direction is 8 angstrom. 8 angstrom means you have 1/8, 1/8, 0.125, which means that small. You get it? So the longer one, like a shorter one, reciprocal space lattice is longer, and the longer one, reciprocal lattice vector is shorter, but still the direction is perpendicular to that plane. So think about it. You have a 100 plane. 100 plane, d spacing is same as the A. Right? A. For example, you have a 4 angstrom. For example, you have a d spacing is 4 angstrom. And then reciprocal vector is 4 angstrom, is a 1/this, 0.25. 110 is 1/√2. So 1/√2, the reciprocal of this, √2. So that means you get the longer. You understand that? So you have two information. It's a length, magnitude, and the direction that tells all this reciprocal space. Okay? So what they mean is you can describe all the planes are two different ways. Vector. Your vector describes the origin to end point by arrow. That's what most of people draw. Vector by arrow. You see? So origin is a certain origin of your vector, and then this end point, and that's a vector, then tells, okay, this length of this vector is perpendicular to the plane. Length of this vector is a d spacing, reciprocal in d spacing. But if you draw the arrows, your 1,000 arrows, can you draw 1,000 arrows? Are messy. So that means it's easy to describe these arrows. Ignore all the arrows. Just draw the origin and end point. Okay? You draw the end point and origin. Then any point you want to draw the line, draw one line, that is the direction. So that's why making all the reciprocal lattice is the plane, all the planes of what you are considering, but only considering end point. You get it? You get the end point. So what they mean here, I skipped it very fast here. Okay, let me see. Come back to this original one. Let's see, original drawing here. Okay, so I want to draw this plane. Okay, I draw this plane. And then when you draw this plane, I have to have origin. Origin of the reciprocal vector, let's see, origin is here. You need the origin. I need this plane, okay, this plane described by direction and magnitude. The direction is, because of this direction, that is the direction. You get it? The direction is going to be that direction, or that direction is a positive direction and negative direction. But magnitude is reciprocal of this magnitude. So that means your arrow is this arrow. You get it? That's arrow. That's a vector. But we actually skipped arrow. We just wrote end point only. End point, and origin. 2, 0, 0 plane is, this is 2, 0, 0 plane. This spacing is 1/2 of the 1, 0, 0. Is that correct? But the direction is same. Because the perpendicular direction, same direction, but this spacing is half of it. But real space half, but reciprocal space twice. So vector is twice longer. So twice longer vector here, but you don't want to draw those vector arrow because that's messy. So I want to just skip all the arrow and then draw end point only. You get it? Is it clear? Then you 3, 0, 0, same way. 4, 0, 0, same way. This all the plane, you can draw it. You can have 5, 0, 0, 6, 0, 0. You can make the 0, 0, 4, 0, 0, 5. You can draw infinite number of planes, and then creating lattice. And then you make this one is collection all the reciprocal space lattice point that form reciprocal space lattice. Not the real space lattice I draw, this reciprocal lattice, but reciprocal lattice each point and not atomic position, that is planes. You get it? That's all the planes are reciprocal lattice point, but end point of the vector. Everything clear now? Okay. So you can draw, this is a 1, 0, 0 direction, and you can draw this 2, 0, 0, 3, 0, 0, 4, 0, 0. You can draw this direction. And then 1, 1, 0 plane is 1 on this direction. You can draw same way. 1 on 0 is 1 on 0 here, and 2 0, 3 0, 4 0. You can draw this, and then you can make all the planes. But this is all two-dimensional. But you have a three-dimensional lattice, actually point all of them in three-dimensional lattice. Okay? But it's drawing three-dimensional lattice, all the points, so complicated. That's why when you describe your writing papers, when you scan, you call two-dimensional cut of the reciprocal lattice. Which means, these are slice of this slice, is this one, h equal 1, L equal 1, L and H. Okay? This, the first one H, and last one is L. But direction of that direction is penetrating that plane. That is another 1, 2, 3, you have another one. But you just make a one slice, not three-dimensional one. Because three-dimensional one is very hard to draw, so I just care one cut. That's what you have. Okay? So most of the reciprocal lattice, you actually see the papers, you describe your samples, you just cut it certain slice of reciprocal lattice. And when you cut the slice, you don't want to show all of them because your diffractometer cannot access all of those. Because your real space angle, you cannot reach certain angle to theta value, you cannot reach the certain chi angle, you can reach, so you can maybe access only this much. You cannot access this, maybe within circle, within that area. Get it? So sometimes your access point may be this much, and this much shape. It's a very funny shape. But you can only access certain planes, your diffraction. Looks like you can access everything, but your diffraction, you mount your sample in certain ways, and your wavelengths or two theta values and d spacing, those things limit actual space of this you can access. Okay? But that's a different business, but I think I'm going to talk about here, and the concept of reciprocal space lattice is planes. And description of plane, very simple way, all the reciprocal vector, length of vector is the inverse reciprocal of the d spacing, and direction perpendicular to the plane. But you have other types of properties, but I think those things not as important as those two. Okay, so then I talk about here. Okay, let's go. And then so far everybody understand concept reciprocalities? Then come back again. All right. So you describe this one two-dimensional cut H, which means that direction of plane, and L, this direction of plane, and then this one substrate we superimpose two different lattices. When you superimpose two different lattices and substrate cubic, and then cube at the 1 over cube is pink of, this blue one, and you have this kind of square. Okay, you square, and this is 1, 0, 0, and 0, 0, 1, 2, 0, 0, 3, 0, 0, 4, 0, 0, 1, 0, 0, 2, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, 4. Okay. L value. 1, 0, 0, 2, 0, 0, 3, 0, the H value. Okay? And then this one going both H and L. So 1, 1, 0, 2, 2, 0. This one 1, 0, 2. Because H equal 1, L is 2. So this one 1, 0, 2. But this one is 1, 0, 2 plane of the substrate. 1, 0, 2 plane substrate is a direction of perpendicular direction. This arrow, this is a perpendicular direction of 1, 0, 2 plane. 1, 0, 2 plane is, you can draw that, 1, 0, 2 plane is half of this. So half of this like this, right? Half of this plane. Okay? This 1, 0, 2 plane, and then perpendicular direction is that direction. Okay? You get it? I think not this way, I think this one. Okay, this one, you get it? So draw the line here, draw the line here, 1, 0, 2 plane. And then perpendicular direction is that one. Can you grasp it? Grab it? Okay. So this is a 1, 0, 0 plane. The magnitude of this one is reciprocal of the displacement. But this is the tetragonal barium titanate, or this is the tetragonal one, elongated one, and then this direction same, okay, but this direction is longer. So that means 0, 0, 1 for the thin film on top of layer shorter, 2, 0, 0 shorter, everything short. So this is 1, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 4, 0, 0, 5. And then, but H is still same. H is all coherent. So this one and that one, same. No distinction. Is it clear that? Okay. So now you can draw this reciprocal lattice, but with the incoherent, those two superimpose, then doesn't overlap, except origin. Origin is already overlap, but all other ones doesn't overlap because this one doesn't overlap. Why? Because you have this length is stay here of the blue, but this one is longer, right? Longer, then that has to be reciprocal shorter, but the direction of plane, perpendicular direction is same direction. You get it? And this one, same thing. This one is shorter, is longer, but not as long as this one, because it's not compressed, it's this long. So that means you actually see that this spacing is of this one small splitting, and then this one more splitting. So when you do this kind of X-ray diffraction, normally you do X-ray diffraction of thin films, and you scan only this direction. Okay, you scan only that direction. When you do scan that direction, what you will see, peak, no peak, suddenly you have two peaks. Okay. Splitting of those two peaks, one coming from here, this film, other peak here coming from the substrate. Your substrate is a lot thicker than your thin film, then this peak very strong, this peak is weak. but you see the splitting of this peak. Then from that, you know what the despacing, you can calculate it. And you scan longer, you get the 001, you can 002, 003, you're splitting bigger and bigger. When you go higher angle, splitting bigger, bigger. That's why sometimes you want to use a higher angle to see the peak splitting. Low angle is closer, and higher angle more splitting. Okay, this is exactly what you get theta 2 theta scan looks like in powder. But when you look at this one, same thing. You scan here, but those two peaks are closer. Okay, sometimes those two peaks kind of overlaps because they're so close to each other. When you go high angle, you can split. But you know from this, and you know from this, okay, I know what the lattice parameter is, but I have no information about from this scan and this scan. I have no idea coherent or incoherent, or relaxed or relaxed. In order to access this, you have to scan not this one, you have to look at this one. You look at this one, you have these two, not the same line, this one same line. So you only looking at regular powder diffractometer scan, you only scan that direction, and then from this and this, you only get information, out of plane lattice information, but you have no idea coherent, incoherent. So in order to access this, I want to access 101 reflection. 101 reflection. This one is 001 reflection. 001 reflection, looking at it, you have no idea coherent or incoherent. In order to access non-001 reflection, you have to move your sample other orientation, which is required under the motors. Okay? So you want to access this. You can see that this one and this one and this one very similar, except one is separation is different, but it's all lined up. So you want to access this, then you'll either line up or not line up. Coherent and incoherent, which is coming from this layer and that layer, is not line up or line up. You can see the coherent, incoherent. And then your separation between these two and separation between these two, and this separation is bigger and separation this one shorter, then you got those information how much of your strain. And from this, for example, these two, I can immediately say between these two, this separation is get bigger when you relaxed. When you have coherent, when you have like a coherent, the separation is shorter, right? Separation is shorter, and then is coherent is separation shorter, then it's what tells is very similar to separation for the coherent is, and in this one, okay, coherent case, you have this separation is further than, and it's incoherent. Then you know that this is compressed strain or tensile strain. Your compressive case, then you're elongated. And tensile case is actually shrink. So from this, you change of this distance from shorter to longer, then you immediately can tell compressive and tensile too. You understand that? Also, at the same time, this position, from this position, and then you also can tell the two. Because this one is a higher value of this, which means your despacing of this one is going to be shorter. You understand that? So this one higher value and despacing shorter, which means your material, the layer grow on top, is smaller lattice parameter. It's the opposite of this case. This case, look at that, your thin film one on top of this is a relaxed one, is going to smaller value of H. But this value, larger value H. And then this one separation is get bigger. So from this, I can tell right away, this material is material growing on top is smaller lattice parameter, smaller volume than your thin film, your boxing, the thin or substrate material. Understand that? It's too complicated?
Sir, can you please explain the color contrast?
Can you speak up?
Can you please explain the color contrast?
Color contrast? Okay, color contrast intensity. Color contrast intensity. So the black here is a strong intensity red. The color contour is actually intensity drops. Because this one is a here very strong peak, and then go down and intensity like this. Intensity like a mountain shape. But the shape is not symmetrical. Because the reason it's symmetrical is many reasons. One is coming from actual this focus space shape, which is strain or peak broadening due to thickness or whatever lattice parameter variance, or you have your instrument, your X-ray instrument has a certain characteristics of the peak coming from. So this kind of length is not intrinsic. That's coming from the diffractometer. Okay, because your detector is longer elongated, so the direction is longer. So it's not intrinsic one. So you want to, in this case, you want to know exact position of this, and position of that's more meaningful. But this elongation is important here.
Broadening in useful.
So the broadening is important. The broadening that direction is important. Broadening is important, not this one. Okay, broadening that one is a rocking curve broadening, and this one is the strain or thickness or those kind of things. So usually you can see that in some other case. Look at this one, very sharp, very tiny, which means you have no broadening in that direction, no broadening in this one. Substrate, single crystal substrate, almost no mosaic spread. And then you have an intensity very bright here, very strong. You're actually starting from green to red, red, and another yellow. That means it's no color to make it, but to increase that intensity. So intensity maybe millions count, maybe here maybe 1,000 count or something. Okay? So now you have a lot of information. This one is from here to here. This one is all lined up. The thin film is all lined up. With respect to the substrate, the reason you have this one is actual tilting of the sample. It's not related to relaxation or anything, just simply tilting of the material. So you can tell either tilting, or you're coming for relaxation, or you can actually tell. I mean, I'm not going to go all the details of this, but you're accessing here, you're accessing one of those. So when you scan reciprocity mapping, you usually do not scan this one, you usually scan one of these. Which one you pick, you get the best separation, strongest intensity, reflection, and then you have a best resolution. Usually, you get your sample is facing here. I'll look at later. I'll show the geometry of it. You get the lower chi angle. Your resolution is 4. So you get the higher, close to 90 degree chi is better. But if you go high chi angle, then you have a less resolution of the D-spacing in the H. So that's why usually most of them people use a 101, 101 or 102 reflection, which is a low index of X peak, which is stronger intensity, and also geometry is more favorable. Okay, which means lack of 45 degree. So I'll show you later. I'm going to go next level, then we can talk about it. Any more questions?
So can you go back to the previous slide? So sir, each of these sharp peaks are corresponding to one of the reciprocal lattice points, right?
Yeah, this one, all of them coming from same, because these 3 layers, very similar size unit cell. That means the same family of like a 101 type of reflection. 101 substrate, 101 strain layer, 101 reflection layer, the relaxed layer, all 3 layers, and they're coming from.
So sir, why is there not a sharp peak in the middle section?
Here, this one is film. Because this film, strain layer is this layer. Okay, you see that this strain layer, I can immediately tell this one is the film. Intensity very weak. Okay, intensity is very strong like this, I can tell substrate. And this one, intensity is weak, I can tell film. Okay, so, and also when you scan this one, you align substrate 100 actually here. Because when you do this H100, where you want a reference value, I want to put 100 here, substrate 100. And then your film is 1.02, which is 1.02 means is with respect to 100 of the substrate. Because you know this one is 100 for the despacing of the substrate. And then 102 with respect to despacing of this one. Okay? Right. So now clear? Can you move next stage? Okay, so now we have tilting and mosaic spread. This kind of mosaic spread. Okay? Mosaic spread is you have this kind of tilting. The Y, you have this kind of tilting here, and then you have this one. Your diffraction is this kind of mosaic spread. And then you have tilting this sample, meet the diffraction condition of that one, but this one you lose the diffraction condition. And in order to make this diffraction condition, I have to move this way. But you lose this one diffraction condition. So you have to make this kind, we call this rocking. Rocking means you roll back and forth, rocking, and then you rock this one to meet the diffraction condition of certain grains. But this grain is only 2, but grains of the many grains like this, then you have this kind of spread of this. And you see the peak width. From the width of this peak, we scan that direction, and then this H scan, it's a just simple scan. Then you see the peak broadening. This is called rocking curve. Width, full width at half maximum. It's an intensity width at the half of the peak height. What the width of it? That's the FWHM of the rocking curve of particular refraction. That is the a kind of index of the crystalline quality. Especially your mosaic spread bigger, you spread it big, mosaic spread small, and spread very small. Like you have a brick wall, very nice brick wall, then there's a very sharp peak, but your mosaic spread bad, your peak broad. Okay, that's one way you can tell, and you see that how big mosaic spread compared to substrate. Okay, you get it? But still, this one is, you see that? This one, H equals 0. This scan is H equals 0 scan, this scan. Okay? Not this scan. Because this one, you see, 200, this scan is that scan. Can you see that? So you can do multiple reciprocal space scan. And you can access this one or this one. This is a 4, right? 4. So this one around scan here. Okay? 4004 scan. 400 scan, you have this one over here and this one over here. And then this one, you get information about this. It's this one and this one. Okay? So you have a lot of information on mosaic spread, but I think most of people use a mosaic spread 00L scan and one of them, and then measure the width of this. That's the mosaic spread. And at the same time, that is constant variation, as I said, here, here, and here, your variation. That variation coming from vertical direction. The vertical direction is elongation here, because of this top part here, the larger, like a reciprocal lattice vector, correspond to shorter real space vector. Real space, this component coming from here, and this component coming from here. Got it? Because this one is a variation of, okay, just a variation of the d-spacing along that direction. So the longer one, reciprocal space of this plane, is shorter, so that contributes to bottom part of the reciprocal space, and this one contributes to top part of it. So when you look at this, and then you have some kind of this one, the variation of this. You can actually see the variation of lattice parameter, and then multi-layers you can see. So we can do lattice constant variation, strain information from reciprocal mapping. Okay, you got this one? Okay, so today it's all learning about structure thing, and then finite size effect. The grain size gets smaller and smaller, and the elongation that direction. So this thickness gets thinner, very, very thin. Then this one elongated. Okay, but elongation still in the same plane. Okay, the same plane, only single layer here, and then all the finite size effect and all coherent, and you get this kind of alignment. So you can separate. It's coming from size effect, coming from the other one, and you can get all this one. I think I'm not going to go all the comparison of it, but I think conceptually you can get this one picture. And finite size effect, you can see that some kind of the broadening of this peak, and then I'm not going to talk about this one and the nanostructuring, but I think we have to think about this. And then you have, when you make a structure, nanostructure very, very small, then you get something super lattice like a structure, but I'm not going to talk about it. Okay, so next one is we learned the reciprocal space. And then we also learned the lattices. We also learned your X-ray generation or X-ray type. And then this one is we call Ewald sphere construction, which is very simple geometric description of diffraction work. So look at this. This is an actual sphere. You draw the sphere, and then this is called Ewald sphere. Okay, and this sphere radius is 1 over lambda. So that means your wavelength of the X-ray beam you use is a longer wavelength X-ray, and then this Ewald sphere gets smaller. And then your wavelengths get shorter, Ewald sphere bigger. So that means your electron diffraction X-ray electron beam is like a 300 kV or 100 kV electron diffraction, and your wavelength extremely short. That's why you can resolve atomic actually positions. Like size of atoms, you can actually see that because your resolution is very good because the electron beam wavelength is 0.01 angstrom or something very, very small. Wavelength gets smaller, 100 times smaller, then this sphere, like an infinite, very huge. That means it doesn't look like a sphere, like almost flat. See that? Getting flat. Then you're flat, then you have a different type of diffraction condition, because I'll talk about here lambda, but you put it in your sample here, and this sample has a plane. Okay? A plane. This plane can rotate the plane like this, and your theta and 2 theta, your geometry, you can make like this. The instant beam coming from here, X-ray tube sitting here, and detector sitting here, and this theta angle, you have another theta angle here, but you have 2 theta angle here. Okay? So I'm going to do volunteers. I need 2 people. Do you have any stick here? No stick? No stick. Okay, let me just use these 2 in the water bottle, and then can you come, 2 of you guys? Okay. And then I want to show you what the diffraction is. So hold this one, come up here. The X-ray geometry usually drawing here. Okay, hold it here. And this is a sample. Your D-spacing like this. So the X-ray diffraction, hold this one, hold this. The drawing I show you Bragg diffraction is sample fixed. Sample fixed, and the way you do is a 0 degree, 0 to increase the angle, both of them, increase it. You have to touch each other. Then the theta angle, both sides exact same. Okay, this is called theta scan. It increases furthermore, like this. What's the maximum theta you can go? 90. Okay, 90. You can go 90 is the maximum because this one is touching each other. But you cannot go 90 because here bulky one attached. So you cannot go 90, maybe 70 or 65. Okay? So this is theta scan. And the theta scan is not common geometry of your diffractometer. Except you need some sample you don't want to move. Whenever you do not want to move your sample, liquid, or something you can spill. So in that case, you want to fix the sample, don't move. Okay, can you try it? So you do this move, 0 degree to here, then certainly peak, multiple peak comes out. Okay, this is because theta scan. Thank you. So now here, no, I haven't finished yet. Okay, like this. Okay, you got it? But here, this guy is X-ray tube. What is attached to X-ray tube? What is attached to X-ray tube? Water line. High voltage water line. Water line, everything attached to here. And everything is perfectly aligned with the tube. And these heavy, bulky ones, you don't want to move this every time. So ideally, I don't want to move this. I want to fix this. Okay? I want to move this. I want to fix it. I want to simulate this one. Same way. How can you simulate this? The way you can simulate it, I fixed this. Okay? Sitting here. How can you move this angle? I have to move my sample. Okay? Instead, I move this twice. You get it? So I move this one and twice, but this still angle, these two angles are equal. Got it? So that means move this one. What is the maximum angle this one can go? What is maximum angle? What's the maximum angle? 180. This one is the maximum angle 180. This one maximum angle 90. Okay, theta 90, and then this 180. But same thing, you cannot go 180 because it's something attached to here, something attached here, so you cannot go 180. And this one is 90, you cannot go 90 because it's half of this. So most of cases, your powder diffraction, theta and 2 theta scan. That's why you call your all the X-ray diffraction work theta 2 theta scan, not theta scan. Except certain type of liquid with the theta scan. So this one, you see, let's try simulator again. You're fixed, you cannot move, you attach to water and then electricity, everything. So I move this one. So you have double, right? You get it? Okay, 90 degree, you attach to here like this. Okay? You got it? So this is what we call theta 2 theta scan. But let's see that theta 2 theta scan you meet here. Okay, I'll met the diffract condition. And rocking curve is just to move this. Fix this one, you only move this. Okay? Because you have to meet diffraction condition of 13 grains. I have this type of grain or this type of grain does not meet the diffraction condition. I want to meet the diffraction condition. This one meet the diffraction condition. But I have to move this one, but this one doesn't meet the diffraction condition. So you have to move this. There's a rocking curve. Okay? So, thank you very much. Alright. I'll call you later. So you have this theta and 2 theta, your instant beam fixed, move your sample, and then your 2 theta move twice. So theta and 2 theta, the detector is attached here, and then your instant beam here. Now you get it? Okay, so then this sample has all the planes, lots of planes. This lots of planes has what do we have? All the planes reciprocal space point. You can actually reciprocal point this particular one creating reciprocal space. You see that? So this particular unit cell and creating all this plane. You get it? So you get superimpose this kind of sphere and superimpose of this polaris point, and that only one meet surface of your sphere That is the diffraction condition. All these ones does not meet the diffraction condition. And that is something you can see. Move this and gradually move, and you can see the peak. Let me just show you. When you move this one touching this one, whenever you touch this one, peak comes out. Okay? Watch this one. When you do this angle go higher and angle, and you touch this one. You see the angle bigger and bigger? Touching here. You get it? Let's try in the time. Okay? So when your angle get higher and higher, and you touching this one on the surface of your sphere, touching this one your sphere, touching your sphere, touching your sphere, that is comes out. You see, 1, 2, 3, 4. You get it? This is what we call Ewald sphere construction. Ewald sphere means any this cross space point touch the surface of the Ewald sphere. That is a diffraction condition. But whenever you touch it, your angle here, your angle is the theta angle will change, which is a 2 theta angle change. So you draw the 2 theta angle, you do the 2 theta angle, right? The 2 theta angle increase, and then you get this peak. Okay, so this is a simple geometric description of all the diffraction condition, and this one is a single crystal material along this scan. Okay, get it? And then you have a lot of determining D from this angle, and then you have this 2 theta angle here, and the X-ray beam is coming from here, and then this is reflective origin here. But you can draw, what I draw here is actually draw this one differently, but I think this one, origin is here, and this one here, and then this is Bragg, same as the Bragg law. So basically, looking this one, same as n lambda equal 2d sine theta. Because you have lambda, 1 over lambda is what is that? 1 over lambda is what? Is a radius, and the 1 over lambda is a radius, and the theta angle, and this 1 over 2d. So you just use this geometry is equivalent to Bragg law. You see that? This is a Bragg law description in geometry in this focal space. Because you have the length of this vector, okay, this length of vector here, okay, this length of vector is what? Length of vector is d spacing, okay, 1 over d spacing. So 1 over d spacing is that one, and the 1 over lambda, and the theta, so that's exactly description. So you see instant beam coming in and diffractive beam coming in, and then you have this kind of, some kind of instrument effect, divergency, and then I'm not going to talk about this. Okay, so we have spectrum of this, and then the purity of this. I think we'll skip this one. Okay, so single crystal to powder diffraction. Okay, you have a single crystal powder. The different single crystal powder, single crystal only one grain, and then this focal space looks like this. You have a 2 grain, looks like this, 3 grain, 4 grain, 5 grain, 6 grain, you grow many grains, look like this. You see, the grain is all the grains randomly oriented. It forms this focus lattice point of the particular HKL forms sphere. See? Sphere. So what they mean is your grain, one grain pointing is one grain single crystal like this, and then vector endpoint is here. But your grain is all orientation possible, then the orientation all possible, and the point of this one forms what? Sphere. Okay? Your sphere and your sphere, two spheres touching each other, what does it form? Two spheres interpenetrating, touching each other. What is the intercept of this? Intersection of it, what it forms? Circle. You get it? One sphere, another sphere touching each other, interpenetrating, it forms a sphere. Okay? A sphere. Rather than single crystal case, it's a diffraction, one sphere to a lot of points forming one point. So X-ray beam coming through that point. So that's a single beam. But when you X-ray beam coming through the cross-section, intersection of sphere, what the shape looks like? What the shape looks like? Cone. Cone shape. You know the cone shape? Cone? Have you ever done like an ice cream cone? Different ice creams, like a bigger ice cream, sugar, the waffle cone, and then sugar cone. It's a different shape. And the different cones. One cone is like a large cone like this, small cone, narrow cone like this, medium cone like this. So cone is coming, multiple cones. And then that is, you have a lot of planes. Each plane corresponds to this 100 and 110, and you have a different family of this, you see? Different family of initially it's a 100, the next one is 110 and 111. You have a multiple one. They contribute to this kind of sphere, and this sphere to this sphere intersecting, and then you have this one touching all of those. But this one is basically forming cone shape. Whenever you cone shape, and then it forms this kind of cone. Okay? You have this kind of cone, small cone and large cones, and then those cones touching this kind of film around. This is a device shadow camera. But usually your X-ray refraction is scanned along that direction. That's why you peak here in that direction. First peak and second peak is touching each other. Okay? So that's a device shadow camera, and then basically you see shadow the cone, one cone, second cone, and then next cone. But this X-ray diffractometer, basically it is a theta, two theta direction. So you can see that single peak, next peak. And all days you put it in films like this. And look at the films and image the film like this. Okay? But now you don't use a film, you use an actual simulation detector. The detector can tell intensity mapping and this one. Okay? So what I'm saying here is a powder diffraction. You don't have to actually rotate your sample. The powder itself rotate your sample. Powder itself automatically rotate. You can access all the planes. That's why rather than mounting single crystal and then you actually rotate, find the peaks you want, you just grind it, make everything available, then look at all the points, look at all the cones. That's all you do. That's a powder diffraction. Okay? So that's what this diffraction is simply, without rotating this one, is just sample is fixed like this. Okay? Sample is fixed, not doing anything. You're just scanning, look at all axes. Okay? So that's all the peaks. But in the single crystal, as I said, single crystal case here, these things you cannot access. You can only access only that one. You get it? You can only access 100, 200, 30, 400. You only that line. You can access only this one. But this one coming from the same plane. Same plane. 100, 200, 300 is all the same plane. You cannot access any of these affects this one. But in powder diffraction is you can see all these things. So you can actually have this one is 100, this one 110, 111. You have all this possible. We can access all. The powder diffraction is you don't need to move your sample, only theta to theta is enough. But in actual thin films, you need to access all of those. So you need to use, we call, full circle X-ray diffraction. And then in order to access this, you mount your sample, and then this is actual theta, motion of theta. But you mount your sample, you actually spin this, and you can lock this one. Okay, so locking this one, this is called phi, and you have, this one is chi, you have a chi angle. You see, this can you see this line? Originally this one sitting here, and move this angle. Can you see that? So you can, originally this line is here, I'm moving this one to go in that direction. Okay, this is axis here, and the phi axis, rotation axis is still the same, but you see this one going down. So this one is original normal scan of this, but we can go this way or even go this way. This one is 90 degree to 0 degree, you can do that. Okay, so that's one, 4 different angles. So can you come up 2 lines again? So I'm going to draw. So here, this X-ray beam is all this one up here. So we did it. Last time I did it this way. Okay, we did this way. Right? We did this way. Or I did that way. You fix that one. I did this way. Right? Okay. And then when you do this one, I think your X-ray diffractometer is a geometry usually that way. Sample facing that way. Okay. So sample facing that way, that means you don't do this way. You don't do that way. Okay. You get it? Okay, you don't do that way. So I put it in sample this way. Okay, sample that way. You guys moving theta to theta that way. Okay? You get it? So that means usually you guys attach to everything. So you cannot move. So I move this one and move that one. So let's see. Okay, let's go. Let go. I will move this. Can you see that? Okay, that's a theta to theta scan. But you have another degree of freedom when you scan this one. And I want to move this one this way. Can you see that? This is a chi. When you do chi, when you do chi angle, then only access plane parallel to that direction. But when you move that way, you can access plane not this way, plane in that direction. Can you do that? Can you access plane facing this kind of plane, this plane? Can you see that? The plane looks like, I want to draw, I think it's not very good. So you have this one. I have a plane is like this plane. Initially this plane, but I want to access this plane. You know, to access this plane, and how can I access this plane? Well, this kind of plane, whatever plane. You have this, initially this one, but you know, to access this one, have this one, okay? No, not this one. This kind of plane. How can you access it? Move this one. This position is original position like this. See that? Can you see that one? This plane? You know, to access this plane, original position here, move this one, this plane, this position. Can you see that? Too complicated? Anybody have more iPhone? Let's get borrow iPhones. Oh, yeah, okay. Good. So you have a plane, more than one plane. So this is a 001 plane. And this plane is 100 plane. I want to access this plane. And then I have to go to original position like this. You know, do that, sitting here, you know, to go there, move that way. Okay, can you see that? So I have this. Now this is the plane I'm accessing. I want to access this. Only way I can do it. Can you see that? I lose this, but I gain this. Okay? I lose this, gain this. So then you get this peak, but this peak, this one, this plane, only every 90 degree. But you get the 101 plane, it's not everywhere. This 101 plane is like every 90 degree. I think you have to draw it. I think it's more complicated. So you have to access initially this plane to move chi angle to access. How much? This much angle. But if I want to access this plane, I want to change a little bit. If I want to access this one, I have to change a lot. You see that? The chi. So basically your chi, find the peak, which is non-existing here, the off-axis peak. Okay? Then once you have this peak is not everywhere. So you want to access this, after move this, then I have to spin this one. Okay? Spinning is phi. Okay, spinning is phi. Phi can access this. Okay, thank you. I think that's good enough. So phi. So you have again, you have this one. I lock this, but you can also spin this. Okay, this is phi. This is phi. And phi 360 degree phi, but this one only can go 90. This one chi. This one phi, theta, and 2 theta. You get it? Okay, good. Thank you. So we have a iPhone. You have to think it. Yeah. So we have this access of this one, and this one allow you to do your diffraction of this plane. So I'm going to show you a couple of actually animation movie, and then okay, so look at this. This is a motion of like a phi motion. Phi motion, you can see this peak, this plane is always available for the reflection. Okay, so when I do this one, can I come over here one more time? So you have this one. You have this kind of. I met the diffraction condition. I already met the diffraction condition. This one down. If I rotate this, does it change? Always this plane is perpendicular that direction is always available, right? Okay, phi. So that means if you do this phi rotation, intensity always same. No change in this case. Okay, you got it? Now you move this one from here to here, you rotate phi. It's different. That's the next movie I'm going to show you. Thank you. Next movie is a little complicated understanding, but I'm accessing here this plane. You see that this plane? This is a 001 plane. Okay. Next movie is this one. You see inside, you see that this plane, 101 plane? Okay, when a 101 plane, look at this blue one comes out every 90 degrees. Is the blue one can come out? Okay, so let me just try again. So this one is instant beam, and then diffractive beam, and diffractive beam, and diffractive beam. Whenever diffractive beam, you will see certain plane is perpendicular here. I want to play several times, and then look at it very carefully. You have this plane. How many of these? One here, one there. You have multiple one inside. I draw only 4 because 4 101 plane, 4 family of them you have. And when you rotate this phi, every 90 degree of phi, it meet the diffraction condition. It comes out here. It's very hard to draw those things by 3-dimensional. I made this one, but actually you can draw something. You can make a box. I think what you could do, you can just make your box, transparent box. Okay, you can make a transparent acrylic box, and then I think I made this, and then for my class, sometimes you make this white paper inside like this. and multiple one, cross-sectioning one. And you rotate this, and you'll see that. Let me try it again. So here, look at that. Can you see the plane? Can you see the white, green line? You can see the green line? You can see the green line? Another green line? I think. Okay, let's try again. There's a plane shows up here, one. See? See this one? So this one coming every 90 degrees. So this one is, peak is not facing the surface, is off axis. This is called off axis peak. And from those, you will be able to know what is the symmetry of your material. Your symmetry is perfectly cubic. Then you see every 90 degrees. You have a 2-4 symmetry, then you will see every 180 degrees. You have a 6-4 symmetry, you get every 60 degrees. So with symmetry, you can actually see that. And then also, you know what is the in-plane mosaic spread, which means, I have your iPhone one more time. You have this kind of mosaic spread. You have mosaic spread, I show you here. This is a mosaic spread, the buildings, right? It's an outer plane mosaic spread. But this mosaic spread plus you have an in-plane mosaic spread like this. Okay? This one and plus this one. You have two. This one can be accessed by rocking curve, but this one cannot be accessed by rocking curve. This one can be accessed by this kind of off-axis. Okay? So the other one is some of the superconductivity people make this bicrystal work, like growing films on bicrystal, measure the transport across the grain boundaries. And then the way they make the bicrystals, you take crystals like perfect like this. You actually polish this one certain angle and fuse it together. Okay? You fuse this together, this one is misoriented like this. Okay, 2 bicrystal. One crystal, another crystal, you have like, oh, I want to make 24 degree bicrystal. You make this one. And how do you know this 24 degrees? How do you know your thin film grown it is all epitaxially grown bicrystals? In order to do that, you can do the same thing. You can do the phi scan, can see these two. So one example of the phi scans. So do you want to play more, or I think it's okay? Everybody understand this? I scan? So when you have this one, so when you have this scan, phi equals 0, and then this one, I think this one is the other one, this is a different one. But look at this one, bicrystals, when you scan the bicrystal, 9-degree bicrystals, it comes out single crystal coming every 90 degree, the phi. Okay? Coming every 90 degree, 1, 2, 3, 4. This strontium titanate single crystal, you scan phi scan, you get 1, 2, 3, 4. But when you scan the bicrystals, 9 degree, then one crystal contribute to this, another crystal contribute this. The separation of those two, 9 degree, and this 24 degree bicrystal, this one, that one, that one, that one coming from one crystal, and this one, this one, this one, this one coming from next crystal. We actually focus the X-ray in the middle of the bicrystal. Then you can actually see exactly separation of those peaks. So that's a 24 degree bicrystal. And then the width of this peak, or this width of this peak, that is the information how much of in-plane mosaic spread, like this. In-plane mosaic spread, okay, not this one and this one. You see that? Okay, you see this? So this full circle X-ray diffraction and thin film X-ray diffraction, you need to access all the Fourier space lattice point as possible, but not everything accessible. And then your structure is when you grow your thin film, you grow materials. And you want to know what you get. So information you need is, once you grow thin crystals, or your thin films, your composition is correct. Your composition is same as what you expected, and then chemical composition. Those things can be done chemical analysis by electron microprobe or WDS or Rutherford back scattering or SIMS and XPS and all these methods. You can do that. But that's a chemical element. So you want to know your structure you grow is the right structure, and then your material grown is epitaxial or not. Use epitaxy, which is what kind of epitaxial arrangement with respect to the substrate. Okay, your relationship between substrate and your film, what is the epitaxial relationship? And then the film you grow on top, coherent or incoherent. Okay, you want to measure strain relationship. And then when you grow this, your crystalline quality is good or bad. Good crystalline quality is measured rocking curve out of eye scans, or you have a grow this one, it's really single crystal, or a bicrystal, you grow some multi-domain crystals, you want to determine this, and you get the size of this, or thickness distribution, you get this, and all these things you can get from this diffraction work. And once you get this one, X-ray diffraction, nice thing about X-ray diffraction, non-destructive, very fast. You take your sample, put it in X-ray diffractometer, you scan it, and you get what you need. After you get the X-ray diffraction, you can do transport measurement, you can magnetic measurement, you can do all these things, AFM measurement, everything. But structure information of a technique like TEM, you have to destroy your sample. So once you destroy your sample, you cannot measure transport again. Sometimes it's too late. When you measure at TEM, oh, I missed this measurement. Or let me ask you this measurement again. Oh, sample doesn't exist. And try to make other one, you cannot reproduce somehow. Doesn't work that way. And then, so that's why you want to get to this X-ray is so powerful. Measure all this measurement before you do non-destructive method, and as much as information. The other thing about this X-ray diffraction is your feedback is so fast. You measure it, but it's a nice thing about your thing is, oh, your structure is imagination, what the structure, and then during your measurement, real time, you can think about this too. The reason I want to do this way is you take X-ray diffraction work and then sit down and then later look at the data, go back again, and then you have to realign it, everything. So it's the most ideal thing is you measure, during the measurement, you know what it is. And then I want to get additional information, to different scan. So you complete mapping of your structure doing one measurement your sample. And that's the most efficient way of the structural calculation. Once you get the structural calculation, for example, okay, I have strain is along that direction and this direction, you can pattern of your sample, whole measurement bar and 4-point measurement bar, and particular direction of applying electric field and magnetic field, you have to do anisotropy measurement of your single crystal epitaxial thin films. You have to know which direction. And this direction, understanding that direction, is coming from your X-ray diffraction. I didn't talk about this one, the real one, but it's the same kind of concept. You know the symmetry. You have two-fold symmetry. Which direction is orthorhombic 1, 0, 0 direction, orthorhombic 0, 1 direction, 0, 1 direction. You can actually determine this by X-ray diffraction. So I think our talk about today is like a general basics of structural correlation. I'm going to use some of this data tomorrow and then until Thursday. I give more lectures about the real example of the use of this. But I think today I just give enough like a basics of structural correlation by X-ray. It's a more general. I mean, I will talk about more like advanced X-ray refraction, synchrotron, and surface refraction, all these things. But maybe that's not immediately need for your sample optimization of your thin films, and that's why I covered that one. I think that's pretty much enough for basics, but we want to know more about this, and then feel free to come and talk to me. I'm available until 1 o'clock here, so about 15 minutes or 20 minutes we can spend time, and then we can go from there. Is there any questions about today's lecture? %? Understand? What percent? I understood 50%, 80%, 90%, 100%. Wow, 100%, good. All right. Okay, so let's do a more informal things, because I know the camera is on and then you don't like to talk, so I think we can shut it off and then we can talk. I know that a lot of students, the camera is shy and then they don't want to be I'm all camera shy too, so. All right. Okay, so let's stop it. And then anything talking tomorrow, I'll talk about some domain engineering or other things. Okay. Feel free to come here and then so we can talk outside.